Hello, everyone, and welcome. My name is Rula Deeb. I'm a senior principal at Geotech in Oakland, California, and the coordinator of the series on behalf of SERDP and ESTCP. Today's webinar focuses on DoD-funded research efforts to investigate the dynamics governing munitions mobility and burial in underground environments. Dr. Carter Duval from the U.S. Naval Research Laboratory will cover the progress to date of SERDP munitions mobility and burial projects. He will also discuss his SERDP project to study munitions mobility and burial in muddy, estuarine, and riverine environments, building on prior SERDP studies in coastal sandy settings. After Carter's 30-minute presentation, we will conclude the webinar with a question and answer period. The next several slides provide instructions on optimizing your webinar experience. If you have not done so already, please download Zoom at the link shown here and provide it to you in your registration confirmation email. If you're unable to download Zoom, you may view the slides using a compatible internet browser such as Firefox, IE, or Edge, and by creating a free Zoom account. If you have an issue with the slides freezing, try keying in Control and F5 to perform a hard refresh of your browser. If you are accessing the audio through your computer, click the arrow next to the Join Audio button, select the speaker and microphone, and please follow the prompts as they appear on the screen. If you continue to experience technical difficulties, call into the conference line shown here or submit a comment using the chat box. Please use that chat box only for comments related to technical difficulties. The Q&A option should be reserved for questions for the speakers. And if you continue to experience technical issues, download a PDF of the slides from the webinar webpage on the SERDP and ESTCP webpage and call into the conference line provided to you in your webinar registration confirmation email. Note that we will also be live streaming the webinar on the SERDP and ESTCP YouTube channel at the link shown here. Today's event will be listen only. You may submit questions by using the Q&A box on the screen. You do not need to wait until the Q&A session to submit your questions. We do encourage you to submit questions well in advance of the Q&A session. And when you do submit your question, please add your organization name at the end of your question so that we can identify you. With that, I would like to introduce Dr. Herb Nelson, who is the Executive Director of SERDP and ESTCP. Herb served as the Program Manager for the Munitions Response Program between 2008 and 2016. And prior to joining SERDP and ESTCP, Herb served as a research chemist and head of the Molecular Dynamics section at the Naval Research Lab in Washington, where his work focused on the detection and classification of buried unexploded ordnance. Herb, please proceed.
Thank you very much, Rula. I would like to add my welcome to you all to Rula's, and I would particularly like to welcome those of you, and there's a significant number of you in the list of attendees that I don't recognize. So that's real good. We're getting attendance from people that are new or just learning about our program. So double welcome to you guys. As Rula made clear, I am filling in for Dr. Dave Bradley, who is the program manager for this area. Dave is off at a munitions conference today and is not having very good luck with the Wi-Fi in the hotel. So I'm the backup. So we'll start with the B team and we'll see where we get. So many of you know these first couple of slides, but I'm hoping that some of you don't, and this will be a good introduction to you. We are really two companion programs. On the left here is SERDP, the Strategic Environmental Research and Development Program, which supports basic research through advanced development in DoD words, or science and technology for many other people's words. We're a program that was created by Congress in 1991, and we're a partnership among DoD, the Department of Energy, DOE, and the Environmental Protection Agency. And you see, we do some fundamental research, but we are also a mission-oriented program, so we're always looking toward the application. The other program that in the companion pair is the Environmental Security Technology Certification Program, ESTCP. And this is what the Department of Defense calls a demonstration validation program, where we take these technologies that were developed by SERDP or developed by some other funding or developed by internal funding of the organization, and we demonstrate them at real world sites on DoD installation. So this program is designed to help us get technology out of the lab into application. We try to establish the cost and performance in real world sites so we can get data that will help us get the word out and get installations using these technologies. Next slide, please. So there are several things that sort of motivate our work. DoD would call that drivers. Others may say motivations. The first of these, of course, is sustaining our ranges, our facilities, and our operations. And you can see some examples here. It ranges from threatened and endangered species in the upper right, the impact of the changing environment and resilience to climate change effects in the lower, I said upper right, I apologize, upper left. The impact of changing climate in the bottom right. A number of things on this way. These are how we keep our forces training and training to fight, excuse me. Next slide, please. The other aspect of what it motivates work at SERDP and ESTCP are these two. The Department of Defense has a significant liability for contamination from past practices. One thing that we help do is handle this liability, these contaminations in a more cost-effective way, either faster and quicker, or faster and quicker and cheaper. And then that's the left-hand side of the slide. And on the right-hand side of the slide is what has classically been called pollution prevention. How can we not add to this liability by adopting more clever, higher tech processes to not generate pollutants in the first place? Next slide, please. So SERDP works in a number of primary focus areas. You can see some of them listed on this slide. I hope nothing that you see here will surprise you, given what we talked about on the last two slides. We have significant efforts in all of these areas. And the one that we're talking about today is munitions remediation, about halfway down the list. But you can see it involves everything from electrical infrastructure to chemicals of emerging concern. Next slide, please. So a significant part of the work of SERDP, but particularly of ESTCP, is technology transfer. It's not a good use of taxpayers' money to develop new technologies, have a great report on the shelf, and not get these things out and get the word out. So you can see all the methods we use for tech transfer. There's all of these output topics can be found on the SERDP and ESTCP website, which is listed at the top of the page. And of course, one of the big parts of this, and we've got it in the middle of this group, is the webinars. You're on one of those today. We hope that will drive you to the website to get some more details or to see analogous projects, and maybe it'll make you come back to more of this in this series. Next slide, please. So here is the next upcoming list of webinar topics. The next munitions response one is coming up somewhere. I've got this written down, July the 28th. So, oh yeah, just made it to the bottom of this list. And that's on UXO detection, classification, and localization in underwater environments. You can see a sampling of all the other focus areas that we've talked about on the slide before in these topics. So mark your calendars if some of those seem interesting. Next slide, please. And of course, this is the link. If you want to know what's scheduled for the rest of the year, you can go to this link on our webpage and find a list as far out as they are scheduled. Next slide, please. So finally, as we leave here, I'd like to remind you that you can get a copy of the presentation at that link. As Rula said early, if you have some trouble somewhere through the webinar, please download the slides and you can follow along at home. Carter will every once in a while tell you where he is on the slides to facilitate that process for you. And now I'd like to turn it over to Carter Duvall.
Great. Let me quickly introduce Carter. Thank you, Herb.
Thank you, ma'am.
Dr. Dr. Carter Duvall is an oceanographer with the U.S. Naval Research Lab. His research focuses on the interactions between anthropogenic objects and seabed morphodynamics, with specific interest in munitions and explosives of concern, or MEC, ripple bed form dynamics, and storm events. Carter's research fuses in-field experimentation, geophysical surveying, time series analyses, morphodynamic modeling, and GIS data analysis and management. He has participated in several MEC research projects, including the Hawaii Undersea Munitions Mapping Assessment and the Bureau of Ocean Energy Management Study titled MEC Survey, Methodology, and In-Field Testing for Wind Energy Areas on the Atlantic Outer Continental Shelf. Carter has served as a co-principal investigator of the 2021 SERDP Project of the Year Award, given to the project titled Further Examining the Role of Cohesive Sediments in Munitions Mobility Through Additional In-Field Deployment of Smart Munitions and Application of a SERDP-developed penetrometer. All right, with that, Carter, we're delighted to have you. Please go ahead.
All right, Rula, thank you very much. So as Rula introduced, my name is Carter Duvall. I work at the U.S. Naval Research Laboratory in Stennis Space Center. And today I'll be talking to you about munitions mobility and burial, looking at the current state of research and considering new directions as we move into new environments with implications in modeling and live site demonstration. So today I'm going to give a brief overview on munitions mobility and burial, touch just lightly on why we're studying the topic, and what are some of the key findings from SERDP studies that have come before, and what remains a topic of interest as we expand into new environments. We consider new parameters such as munitions corrosion and applications at munitions response sites. With that, I'm going to talk a bit about our study, MR21-1227, Parameterizing Munitions Mobility and Burial in Riverine Environments, as we begin to ramp up our field efforts for that study. And then lastly, touch on where we're heading with munitions mobility and burial research moving forward. So why do we study munitions mobility and burial? Well, as many of you are probably aware, munitions are present in U.S. and global waters as a result of live fire testing and training, combat operations, sea disposal, which in the U.S. went up to 1970, as well as periodic accidents. While we have a general idea where the munitions are located, because they've been in the water for decades to half a century or more, there are a number of processes that have been occurring since their deposition. And so to be able to detect, monitor, and if necessary, mitigate for those, we need to know what's happened to them since the time they were in place in the underwater environment. We need to know where to look, whether they were buried or exposed, or whether they can move. And largely it was that last portion, whether they can move, that sort of instigated some of the research with mobility and burial. Many of you might have seen articles such as this pop up in the news from time to time, where somebody went onto a beach after a storm and they found some rusted object, and it turns out to be unexploded ordnance. And invariably in the article it will say they washed ashore. But the question we asked was, did they really wash ashore? And if so, what were the processes that allowed that? Or were they there the whole time and that the beach face just changed because of the storm? It had eroded away to expose those. Since asking those questions, SERDP funded a number of successful studies investigating this and other questions with mobility and burial. So where are we at? Well, here's the synopsis of some of the main parameters that we feel are important with mobility and burial. I've categorized them here into four main categories that we'll go into a little detail with. First, we can look at the munitions and explosives concerns characteristics, things such as the density of the munition, its diameter or caliber, and potentially the effects of shape. Then there are things such as the bed characteristics. Are we on a consolidated hard and rocky bed, which will not allow for burial, or something that's unconsolidated, such as sands or muds? Then, of course, the environmental setting is important as well. Are we in a coastal wave-dominated environment, or are we in a riverine environment with unidirectional currents, or a tidal estuary that might experience both waves and currents? And then, of course, depth. Are we in somewhere shallow where we expect rarely frequent forcing, or somewhere deeper where it's only episodically driven? And lastly, anthropogenic effects. Things such as the method of emplacement. How did the munitions end in the environment in the first place? Was it through live fire, where we have to consider things such as impact burial, or were they simply disposed? And then once in place, what sort of activities might have the potential to expose them or move them around? Things such as dredging or commercial fishing or infrastructure installation as we continue to invest in alternative forms of energy on the continental shelf. So I'll start first with munition characteristics. If there's nothing else that you leave with from this study, although I hope there's several things that you remember and take away, knowing that density is a primary characteristic for mobility and burial is one thing that I want you to take away. And this is really well demonstrated by this image by Joe Calantoni from his study, MR 2320. And what this says is that essentially, if your object is less dense than the sediment that it lies in, it will almost always remain proud after intense transport. And that increases the likelihood for mobility. If the object is more dense than the sediment that it lies in, it will almost always bury after moments of intense transport, which reduces the potential for horizontal mobility. If it is in and around the density of the sediment, you have the potential for partial burial or transport, depending on the conditions. This was also supported by work from Peter Trukowski in MR 2319, where he did indeed find in his study that lighter munitions became mobile, denser munitions became stationary, but in and around the density of the sediment, he saw both burial and mobility, depending on how quickly the waves set up. Diameter is an important thing, caliber of the munition, but one thing that we're definitely looking into as well is the shape of the munition. Now, we feel that shape may be primarily a factor in conditions where mobility is likely. That's going to be where, again, the density of the object is less than the density of the sediment, which doesn't allow for burial, or hard bottoms. This was investigated by Drs. Garcia and Landry in MR 2410, where they conducted a number of tests examining the orientation of the flow relative to inert surrogates and to see how they would orient themselves into the flow and how they would migrate. But what about with burial? Well, Dr. Calantoni in MR 1913-17 is investigating that question right now. We want to see whether or not shape has an effect on burial, and if so, to what degree. To do so, he's comparing the real inert certifies to simple cylindrical instrumented surrogates that have the same density and diameter as the real inert certifies and comparing their burial behavior. If it turns out that they bury in a similar fashion, that means that shape isn't necessarily an important characteristic with burial, and that's one less parameter that we have to consider when we develop our models for burial. With the sediment, as I mentioned before, in consolidated sediments, it's unlikely that we would have burial, but in unconsolidated sediments, there is the likelihood for burial, but it may vary due to the sediment type, whether we're in a cohesive sediment, things such as muds, or non-cohesive sediment. Muds and sands have different transport behavior. It has to do with the cohesive nature of the muds, which requires more energy to erode, but once eroded, is very easily kept in transport, versus sands, where the erosion and the transport threshold are very close to each other. So on the right side, what you see is an idealized graph of how the increasing percentage of mud might influence the anticipated burial mechanisms on the x-axis, and on the y-axis with increasing forcing. So on the left side, if we consider sands, as energy increases, we start to see burial occur through scour processes. This allows for objects to scour and bury to about a depth equivalent to the diameter of the object itself. But as energy increases, we get momentary liquefaction of the seabed, which allows for the objects to settle deeper into the sand through what we call granular sorting. As we increase the percentage of mud, in hard muds, we find that scour is inhibited because of the cohesive nature of the sediment. And in soft muds, the muds themselves may not actually be able to support the weight of the surrogates or of the munitions, which allows them to settle and bury. As energy increases, we get intrusion of fluids into the bed fluidization, which then decreases the bulk density of the sediment and allows the surrogates to, or the munitions to settle deeper into the sediments. Now, even within a sediment type, there can be considerable variability. And this was exemplified by a study conducted by Art Trembanus at the University of Delaware and myself in MR 2730. In this study, we looked at mobility and burial in the lower Delaware Bay estuary. We conducted 4 different deployments at 2 different field sites. One which was characterized as stiff, muddy sands, and a second site that was characterized by soft, sandy muds. At each of the sites, we had a deployment where storm events were observed and a deployment where no storm events were observed. In Site 1, for instance, when no storm events occurred, we saw very little burial. The objects remained mostly proud, and what we saw was likely explained by scour or a little bit of settling. However, in Site 2, with similar conditions, we saw the munitions were almost entirely buried. And this was likely because the soft sediments could not support the weight of the surrogates and they settled into the mud. Now, with Site 1 during storm events, we saw very clear evidence of scour burial. We saw our large 155 millimeter surrogates sitting in open scour pits. But in Site 2, with the similar conditions, we found that the objects were buried much deeper than can be explained by scour burial, and it was likely due to fluidization of the soft muds. As we move into environmental setting, the primary characteristics we have to consider here are, what is our hydrodynamic regime? Are we in a coastal setting where we might anticipate wave-dominated environment? Or are we in a river setting where we have current that are dominating? Or even in a tidal estuary where we might have primarily currents, but also wave energy? And all of these environments are going to have characteristic sediment types, characteristic hydrodynamic forcing regimes, and as we move along the shelf, we move into deeper settings where we may move from more frequent forcing to more episodic forcing. And so eventually we get to the deep water where there's very limited forcing to allow for further processes for scour or mobility and burial. Now, it's in that shallow settings where you would anticipate the most likelihood of processes causing causing mobility and burial. And so it's not surprising that it's in those shallow areas that we've focused the majority of our research in the coastal settings, in the bay estuary settings, and now moving into riverine settings to better characterize mobility and burial. And then lastly, touching on anthropogenic effects, as I mentioned before, the method of deposition is going to be your initial condition. So if we're talking about live fire, we have the potential for impact burial. This is things that are being studied by Dr. Stephen Bless, MR 19-1227, and previously by Dr. Peter Chu. And the condition here is if we have impact burial, it's unlikely that those buried objects are going to be exposed unless there's some sort of significant process that either erodes the sediments or some sort of post-depositional anthropogenic effects, things such as dredging, fishing, and infrastructure installation. And this is exemplified perhaps by this image in the lower right, where you can see a 14-inch round lodged in the drag head of a hopper dredge. So while I've categorized these into neat, discrete groups, the reality of the fact is that these processes are very much interconnected and can't be treated independently, but must be treated together. For instance, if we're in a coastal wave-dominated environment, we have to consider the fact that we might be in a sandy setting. What type of munitions historically have been there? What are their density, their shaping, and caliber? And how were they placed in the environment in the first place? Was it through live fire testing training, or were they disposed of? And it's those considerations that we have to carry over when we move into modeling. The goal here, of course, is to take the field data and provide models that will allow munitions response site managers to understand historically what's happened at their site. So where munitions might be or where they have buried or moved to, and then moving forward, whether there are any things that might induce further burial or mobilization that would make it necessary to mitigate for any circumstances. So much like that interconnected web that I showed in the previous slide, there are probabilistic models such as the underwater munitions expert system model developed by Dr. Sarah Rennie and Alan Brandt and Johns Hopkins ARL that utilize these parametric relationships and these key parameters that we've identified to develop these models for predicting mobility and burial behavior. And these models, as you can see, these independent inputs here are all going to be characteristics of the individual field sites, whether we're in a wave-dominated environment, a current-dominated environment, what the sediment type are, the munition types that are there. So each of those can be tailored to the individual sites that we're concerned with. But because this is a probabilistic model, it requires field and laboratory observations to develop and to validate. And these need to be statistically significant observations, so not just a few, but several observations. And that's why we conduct such detailed field experiments on this topic. There are other models as well that we are developed under the SERDP umbrella. These are things looking at the munition scale processes, things such as the flow around individual munitions and scarabary behavior, and things up to site scale processes, looking at how storms and stuff may affect the bathymetry of the site, the morphology of the site, and the sediment dynamics. And this could be input then into models such as the expert system model to look at site-wide predictions of where we would anticipate the potential for burial and how deep based on the sediment type or the depth or the type of forcing. But as I mentioned before, these models, they need observations to tune and validate. And as we move into new settings and we consider new parameters, these require new observations. And that's where our study comes into it. So parameterizing munitions, mobility, and burial in riverine environments. This is a study that I'm conducting with Dr. Art Trembanis at the University of Delaware and Dr. Carl Friedrichs at the Virginia Institute of Marine Sciences. Now, some of the impetus for the study is really well exemplified by this image here. This is actually an image taken 3 months apart at the Potomac River at Great Falls, Virginia. On the top image, you can see what is categorized as a pretty high discharge event for that section of the Potomac River, about 162,000 cubic feet per second discharge. So you can see quite a raging river. But then 3 months later, we're looking at a setting where there's only 3,600 cubic feet per second discharge. So it's much calmer. So those high discharge events that introduce the potential for there to be mobility and burial at riverine munitions response sites. So that piqued our interest, and we looked in depth at some of the available GIS data and identified at least 288 formerly used defense sites or munition response sites that fell on or near river systems, and 48 of which fall on major river systems. When we went to look in detail, we saw that many of these fall on the lower courses of rivers, the areas that we typically refer to as the zone of transport or the zone of deposition, as exemplified in this diagram on the left. That's not surprising, as these tend to be the areas that are more navigable for the waterways. We then took this data and we extracted the channel gradients and the discharge rate for the sections of rivers near where all these floods or active military installation ranges and training areas are to build this plot here, this parameter space of channel gradient and discharge. And what we see is that there's actually a considerably wide variety of both the gradient and the channel type, and the discharge, which poses an interesting problem. And that's because rivers themselves are quite variable, depending on the antecedent geology and the processes and the time scale of the river's development. And this variability complicates, in some ways, the direct application of those previous observations we have in other environments and the models, the parameterized models that were developed in those other environments. But we can also just flip it on its side and say, well, because there is such wide variability, there are likely instances in a riverine setting where we can apply or modify the existing parameterized relationships to better understand the dynamics that are occurring in river systems. Simple things like we know that on a rock or consolidated bed, we're likely going to have no burial, but mobility is likely. That in unconsolidated beds, we have the potential for burial. And then we have interesting new questions like, in high riverbed erosion scenarios, is mobility or burial likely? If mobility occurs, we would assume that it occurs downstream and downslope. And like sediment dynamics in river systems, we would expect deposition in areas such as deltas and estuaries or off-channel sandbanks and behind man-made impediments such as dams. But this conceptual model needs to be validated by field observations, and then will allow us to modify any existing relevant parameterized models or develop new ones tailored specifically to riverine MRS. And so to do so, we are going to conduct an in situ experiment on or near a riverine munitions response site. The goal of this study specifically is to develop parameterized models, but also to utilize existing literature and real-time observation and operational hydrodynamic modeling that are already in place, and to use those models and networks as inputs for the parameterized models that can then bridge between the available data sets, the available observation networks and models, and probabilistical models such as UNMETs. So to do so, you recall that I said models need quantitatively and statistically significant observations of munitions mobility and burial. So we need to increase the number of observations that we have. In our study, we're doing that by increasing the number of surrogates that we have that we'll put into our field study. We're going to have a suite of both instrumented and simple surrogates. The instrumented surrogates we're leveraging from MR2730, the Delaware Bay study. And these range in size from 60mm mortars, shown in the upper left, to 155mm artillery shells on the right. And these are equipped with internal motion units to record things as roll, pitch, and yaw, and acoustic tags, which allow us to track their position underwater. Now, simple surrogates may be as simple as things such as pipes that are filled to have the same density and diameter as the munitions that they're replicating, those important characteristics that we identified before. And then also by using additive manufacturing to create real shapes to see how those are impacted in cases where we might have mobility. For tracking, we're using an acoustic tracking network that's provided by VEMCO. It's the VEMCO positioning system. This system leverages small acoustic tags that are typically used to track biology and in fisheries studies, and a series of passive acoustic receivers, shown here, when set up in a network, act essentially like an underwater GPS. We use these in the Delaware Bay study with great success to monitor the positions of surrogates on the seabed. This actual image on the lower right shows snippets of where we extracted the tag locations for individual tags in surrogates, both in the tail cone and the nose cone, and measured the distance between both the tag of there to estimate the overall length of the surrogates and compared that to the known length of the surrogates. And we were within a few centimeters for each of these, which demonstrated the precision and accuracy of this method. One thing we're introducing as well is the VEMCO Fathom Line system, which using a data buoy will allow us to monitor the tag's presence or absence in real time. So we can see in real time what events may trigger burial or mobility behavior in the munitions. For field sites, we were looking pretty heavily at the Potomac River because there are a number of formerly used methods or munition response sites along the course of the lower Potomac River and in nearby rivers such as the Pax River. These are sites such as the Naval Support Facility at Indian Head, Quantico, and Dahlgren, as well as on the Pax River, the NAS Pax and Solomon's Annex. We've more or less settled on NSF Indian Head as an ideal site. The other reason why we were looking at the Potomac River is because if you think back to that image I showed you earlier with the high discharge, the recurrence interval for relatively high discharge in this section of the Potomac River is pretty short. We see that discharges in excess of 100,000 cubic feet per second occur only every 1.75 years or so. So this increases the potential that we will be able to observe in the field larger discharge events where we might have the potential for mobility or burial. Our goal is to deploy not one, but two of these VEMCO acoustic grids equipped with sensors to measure the currents and environmental parameters, as well as the suite of simple and smart surrogates. And our goal is to kind of maximize the coverage of potential conditions and parameters. So when we may be deploying at different sites where we have different sediments, different depths, and then we want to compare those in situ measurements to the models that are currently in place for the Potomac River. In fact, this current profile that you see in the upper right of this image, those were extracted from the CBOS model. And what we can do is actually compare those model outputs to what we're measuring in situ and tweak those as inputs for our parameterized models as we develop them. With parameterized models, our goal is to either modify existing models or develop new ones if necessary. And this is kind of an example of what we might be looking at. There's been quite a bit of work conducted on the initiation of motion for objects. And this considers many different sediment types and different forcing, whether waves or unidirectional currents. But what about the effects of channel gradient slope that rivers introduce? Then things such as scour burial. Much of the work is focused, with munitions at least, on waves and currents. So then what happens when we're in a unidirectionally current-dominated environment? And then lastly, things such as fluidization. Much of the work is looking at fluidization under waves. What happens when we're in a river event where we have high discharge that triggers mass erosion? So these are the kinds of things that we'll be adapting and considering as we work to develop these parameterized models. again, with the goal of leveraging these real-time observation networks that are in place, much of which exists on the Potomac River itself, as well as any forecast or hindcast models such as CBOS or with VIMS and Chesterons, and to tune and validate these based off our field observation. So a few further considerations with mobility and burial. As we identified before, it's not just the behavior of the surrogates themselves, but the conditions that they're in, the sediment that they're in that are important. And when it comes to particularly burial, understanding not just the superficial properties of the sediments, but the shallow subsurface properties of sediments as well. To be able to measure that, we have to take in situ penetrometer measurements, and those are conducted by Dr. Nina Stark and her team, for instance, with this drop penetrometer shown on the left. But to extrapolate these site-wide so that we have maximized our coverage from these individual point sampling, we wanted to see whether we could relate those shallow subsurface geotechnical properties that are important to scour and burial behavior to superficial geophysical data, in this case collected by a EdgeTech 6205 phase measuring bathymetric sonar. And this was conducted as part of MR 2014-80. So at the same field sites that we conducted our experiments in the lower Delaware Bay estuary. And what we did was classify our sonar maps based off the backscatter intensity and the sediments on the surface, and then compared those to the measurements of the quasi-static bearing capacities, the bearing capacity of the sediment from the penetrometer. And what we found was that we could pretty strongly link and extrapolate those shallow subsurface properties, such as bearing capacity, to the superficial classified maps. So what this allows us to do then is to extrapolate those point data to wider site-wide characteristics through these geophysical classified maps. And so the implications here being that we can reduce the number of in situ samples that are required while maximizing the coverage as we translate these into munition response sites characterization. And then lastly, one further thing, and as I mentioned before, density is an important predictor, but some new things that are being considered is that these munitions have been underwater for decades. And so biofouling and corrosion becomes an important thing to consider. These are being investigated by Dr. Jack Blair at University of Delaware with his study MR 20-1094. And he's looking at how they may decrease the bulk density of MEC and increase the roughness, which may have implications for burial and behavior over time. So as we continue to expand into new environment types and consider additional parameters, we work to have a more comprehensive understanding of munitions mobility and burial in real-world settings. And so as we continue to develop the models, the next step is to provide control settings to evaluate those models and their predictive capability, and not just for mobility and burial, as we've shown, but also for those important environmental conditions that control or influence mobility and burial. And of course, the reason that we're doing this is to provide munitions response site managers with the tools necessary to understand historically what's happened to their site, to know where to look potentially for munitions, and how over time those might change, and in the future, whether it is necessary to mitigate for mobility or burial. So with that, I want to just quickly acknowledge all of the PIs who have projects with SERDP looking at munitions mobility and burial and the work that I've highlighted here. I strongly encourage you to go into the SERDP website and look at the great research that these people are conducting. Also want to thank SERDP and ESTCP for funding this work. So Dave, Herb, thank you very much, as well as all the folks behind the scenes that help us, such as Sarah and Nobliss, and of course, Rula and your team for putting on these fantastic webinars. So with that, I want to say thank you.
Thank you so much, Carter. And just a reminder for our audience to go ahead and submit questions during the Q&A box at the bottom of your screen. We've received a number of questions, Carter, and we'll relay them to you. For starters, there appears to be a lot of focus on sandy or muddy sites, but you mentioned the potential for sites with consolidated beds increasing the chance for mobility. What environment types would we find this? And are there real-world examples with munitions?
Yes, so that's a great question because we are, as I've talked about, expanding into new environments. These would be situations where we have rocky coastlines and coralline settings, areas in the Caribbean or in Hawaii. There are a number of sites such as Vieques in the Caribbean and in Hawaii, places such as Ordnance Reef, where we have munitions in coralline environments, which poses interesting problems both in the fact that they have maybe no longer mobilized, but start to encrust, which makes detection a bit more interesting of a problem for this environment. So there are definitely conditions where we would anticipate there to be munitions in consolidated beds.
Wonderful, thank you, Carter. If we know that density is a key predictor for mobility and burial, and therefore when burial is expected, what questions remain with mobility and burial that support continued research efforts?
Right, and that's a really good point, because the reality is we do have a generally good idea of when we should anticipate there to be burial, but what we're still trying to understand is those processes that cause burial and to what depths then we would expect burial. So when we talk about working in sites and needing to understand where we might find munitions, for instance, in sites where we're going to be dredging or things like that, we need to know what depth we would anticipate those to be found. And so it's continuing this research, looking at burial to better understand and predict where we will find them and what processes drove that burial so we can better predict that.
Thank you. Okay, a broader question. Munitions in the underwater environment have been underwater for decades, as you mentioned on one of your slides. How do you translate what you observe in these studies on short timescales to the much longer timescales for munitions at response sites?
Right. So much of the stuff that we're able to study in the field is occurring on days to weeks to months scales, but because these munitions have been underwater, there is decades plus of processes that may have acted upon them. But what we are studying is kind of those initial conditions. What happened when those munitions were placed in the water in the first place? So we're trying to understand historically what initially has happened. And then as we begin to translate this to individual munition response sites, we can start to understand better the history of those sites and then understand where we might be able to find the munitions based off of the sediment types that are there, what sort of historical events, whether it be storm events or in rivers, mass discharge events, flooding events. And that helps us better understand then the processes that occurred historically, so we can begin to extrapolate those processes that we're observing in a short period of time over the historic record of the sites. And then the next step of that is, okay, we have the initial conditions that we are looking at as we begin to characterize these munitions response sites. And if we do understand and find the surrogates or the munitions at the site, then moving forward from those initial conditions, do we expect them to, if they're buried, to become exposed and mobilized again? Or if not, will they bury deeper? So it's just a simple matter of, well, not so simple, but it's just translating what we're observing in our studies and extrapolating it to the longer historical record.
Thank you. We all appreciated the overview that you provided in addition to the in-depth look on your actual work. Are you aware of any studies that are evaluating the follow-on effects of climate change with respect to munitions mobility and burial?
That's interesting. I personally don't have any that come to mind off the top of my head, but because of the effects that we would anticipate from climate change, right? So coastal erosion and increased potentially for increased and more intense storms. That is an interesting problem that we have to tackle as we move through this next century. But offhand, I can't say that I know of any studies offhand.
Great, thank you. If you were to look at some of the categories of characteristics that you discussed in your research and others' research, and you had to prioritize them in terms of additional research that is still needed, which of these four categories is the highest priority? Bed characteristics, MEC characteristics, environmental setting, and/or anthropogenic effects?
That's an interesting question, and I would kind of take an easy way out of saying it's really going to depend on the site right? The individual munitions response sites. So as we translate this research from just generic conditions to conditions where we know that we have munitions response sites, that's where we have to start to understand historically those processes that occur to the site, and then prioritize what processes are important. If we're in a very muddy environment, right, it's not going to likely be things like scour burial or granular sorting that's caused the burial that we might observe at that site, and it's going to be things more consistent with what we see in muddy environments. So better understanding the sediments there. So it's hard to say individually what we would prioritize out of that. Now, there is one thing I will say that is, I think, perhaps a little understudied, and just because of the difficulty of replicating that, and that is anthropogenic effects, right? And those are going to be so much dependent on the environment that we're in. And in many cases, it's the anthropogenic effects that we're trying to mitigate for moving forward, like when we're in harbor settings that we need to dredge and better understand the burial that's happened or where the munitions might be, and then what level, what depth that we have to account for those munitions when we dredge. So it's an interesting question, but I don't want to shoehorn it in by saying, well, this is the most important thing. I think it's really dependent upon what type of environment we're studying.
All right, this is a question from the GSI services group. Does the method of delivery impact, that is, or for example, long-range fire to a shallow overwater target versus dump off a boat directly below, does the method have an impact on how soon an item may start to mobilize?
Again, I think that's going to be really dependent upon what the conditions are at the site. I think if you could generalize by saying that if we had impact burial due to long-range testing of, say, artillery or naval guns, right, we would anticipate that in certain scenarios we'd have burial and potentially deep burial. And that reduces the likelihood for mobility, at least from natural processes, unless you have significant erosion. But of course, that doesn't account for anthropogenic sources if we start to dredge or excavate. When you compare that to shallow disposal, much of the disposal that occurred later on was in deeper waters. But in shallower sites, if we had disposal, we wouldn't anticipate significant impact burial necessarily. And so it would be in those scenarios that we might have more likelihood for there to be subsequent mobility after deposition, and then perhaps in a shorter time frame. But again, there are other things that go into that too, because if these are really dense munitions that have been situated in a sandy environment, they aren't going to mobilize probably. They're just going to bury in situ further.
Great, thank you so much. What potential challenges do you foresee conducting an experiment at a munitions response site? And how do you mitigate those challenges? And how do you plan to mitigate those challenges in your future work?
Absolutely. That's a munitions response site for a reason. It's an area where we have that potential risk. And for us, it really comes down to scouting the site in detail and understanding historically where they might be found. And to mitigate that is to conduct these geophysical and geotechnical surveys that will, basically anomaly avoidance. And that's a part of what our study will be. We plan on conducting pretty good surveying of the site to make sure that we're not putting anything down where there's any anomalies, where there's any risk. And that's something that I think we have to deal with in any study where we investigate munitions response sites. But the benefit of being able to conduct experiments at those locations where we're measuring the conditions that occur at those locations and not have to try to replicate them somewhere else is a benefit that I think, as long as we are mitigating the risk properly, that is something that we should, strive towards.
Thank you, Carter. This is a question from Atlantean Technologies, LLC. For sites that are in unique ecosystems like parts of Hawaii, is it possible for munitions wedged in coral crevices to detonate? For example, if an anchor wedges against it after 20 years of being underwater, what are the risks of it getting pulled on?
That's an interesting question. a very specific scenario as well. You know, I don't know that I could have a good answer for that, but obviously you don't want anything potentially impacting the munition. Now it depends to a degree also how the munition ended up there in the first place. You know, does it have its fuses intact? Was it fired or was it disposed of? But again, no impact is ideal impact, right? When it comes to those, because we just don't know what will happen necessarily. But you know, the more that these things are in the water, right, there's also the effects of incrustation, and if they're breached, what happens to the constituent that's inside of it? Are we talking about a you know, conventional weapon, or is it another type of constituent that we have to worry about? So it's a very specific scenario, not an easy question to answer without, you know, looking further into the problem.
Thank you, Carter. You talked a bit about predictive modeling. What can we expect with respect to a timeline for predictive modeling for munitions mobility and burial? How and when can site managers start using predictive models, in your opinion, based on your work and others' work that you've reviewed?
Yeah, I think it's kind of a moving answer, because when it comes to certain cases when we're in sandy, wave, and dominated environments, I think that we're moving very quickly towards having models that we can begin to test, right? And we still need to validate these models. We still need to make sure that they work in the real world settings. And that's what we're moving towards, I think, particularly in the areas that are very well investigated. Again, those kind of coastal wave dominated environments. And you know, as we begin to collect more data in other environments, such as rivers and estuaries, and begin to tailor those models a little bit more, you know, those then will also move towards being able to be tested at live sites and towards production. So I think, you know, we're talking about you know, a matter of a few years that we should hopefully start to strive to have those products in place. You know, but it's a team effort, and it takes a lot of people working on this problem. So it's you know, we're all working towards the solution. That's what we hope to get out of these studies, right? Is to provide these tools, and I think it's going to be here, you know, like I said, sooner than later for certain conditions. And as we continue to improve our knowledge, we'll continue to expand the munitions response types that we'll be able to apply these models to.
Wonderful. This is a question from EPA. How frequently have drop penetrometer studies been conducted at MRS live sites?
For drop penetrometers, I can't say offhand I know how often those have been conducted, and there are other methods of collecting penetrometer measurements besides, you know, free fall drop penetrometers, such as the one by Dr. Stark and her team. But that's where, you know, again, we have to make sure that we are conducting anomaly avoidance and make sure we aren't collecting samples where there are munitions. But this is an important tool for characterizing rapidly as well the subsurface geotechnical properties. And so the whole reason that we're doing this in the SERDP umbrella is to try to apply this penetrometer to munitions response sites. So I'm not sure how much has happened so far, but you know, it's something that I think with proper risk mitigation is a very important tool for characterizing sites.
Thank you, Carter. And thank you for referring to Dr. Nina Stark's work. She gave a webinar on August 5, 2021, and you can access her webinar slides and the recording on the SERDP and ESTCP website. All past webinars have been archived there. And of course, the slides, as with Carter's slides, contain the PI contact information. So feel free to reach out to her for our EPA question for follow-on discussion about your specific question. All right, Carter, we're gonna start wrapping up here. And as we do that, I think we've answered all 12 questions that have come in. What is the last message, takeaway message, would you like to leave our audience with today?
I think that it's just that you know, this is a team effort in many ways. While these are independently operated studies, the SERDP umbrella has really allowed us to come together and work on this problem and share data And this has been very beneficial. And I think it will be as well moving forward as we begin to translate the field data into the models to the munitions response side. So again, I want to thank SERDP for allowing us to conduct this research and really serving as a platform to allow us to collaborate with each other.
Great. Well, thank you so much, Carter. You've done a fantastic job with both the presentation and the Q&A session. With that, just a last reminder that these webinars take place every 2 weeks. So our next webinar will be on Thursday, April 7, and it will feature DoD-funded research efforts to improve wastewater treatment and reuse at DoD facilities. We're going to have 2 speakers, Dr. Chris Griggs from the U.S. Army Engineer Research and Development Center, and Dr. Wei Lau and Chris from the university. Okay, so sorry about that. I blanked on the university name, but the focus of this webinar will be a twofold: the assessment of a baffled bioreactor-based gray water reuse system that is able to harvest 8,000 gallons of fresh water from gray water per day, and then the development of a self-sustainable and scalable organic waste and wastewater treatment system that also produces fresh water and energy by integrating solar, biological, electrochemical, and membrane technologies. Registration is open, so please visit the SERDP and ESTCP webinar webpage to register for this and other webinars through the end of 2022. And before we conclude, I would like to remind you that both the audio and a copy of the presentation of today's session will be archived on our webinar webpage in case you'd like to refer to them in the future. So this will be archived on Carter's webinar webpage, and if you need to refer back to his last slide, which includes his contact info, please feel free to reach out to him with additional questions you may have. At this point, we're going to wrap up and ask you to please consider taking a moment to complete a brief survey that will pop up on your screen at this time. Thank you so much for participating.